Welcome to section 7.2 on the transformations of a single random variable. The goal of this section is to calculate the probability density function for a transformed continuous random variable when possible. Lotus, you remember that's the law of the unconscious statistician, is powerful, but it only lets us calculate expected values of a transformed variable, not probabilities. In order to calculate probabilities, we need the density function of the transformed variable. Lotus does not give that to us. The following theorem, however, tells us that under certain conditions we can find the probability density function of the transformed variable, and the proof gives us a method for doing that. Theorem 7.2.1. Let x be a continuous random variable with probability density function f sub x of x. Remember, capital X refers to the variable x, little x is a value that big X may take, and cumulative density function f sub x of x, big F. Let t be g of x, where g is a one-to-one function, increasing and differentiable. Then the probability density function for t is f sub t of t is f sub x of g inverse of t times g inverse prime of t. Nasty. In fact, I actually don't remember that formula. I always apply the method that we're going to see here in the proof every time that I need to do this. Before we prove it, let's do a little bit of review or recall about why we need some of the conditions that are given in the function and what in the theorem, and what the relationships are between the PDF and the CDF. So the first thing, we need g to be one-to-one and increasing. So if g is one-to-one and increasing, what does that mean for us? Well, first of all, it means that g inverse exists. So that's the first thing. The fact that we've got g inverse here in the statement of the theorem is allowable because g is one-to-one. Because it is increasing, then we've got the following property. If we have g of a is less than or equal to b, then we can apply the inverse and maintain the inequality. So a is less than or equal to g inverse of b. That's a property that we're going to be using in the proof. That's the first thing that we need to remember. The second thing is the cumulative distribution function, f sub x of x, is defined as the probability that x takes values less than or equal to little x. That's the definition. We're going to need that as well. And lastly, we need that the CDF is the antiderivative. So if I take its derivative, I get the PDF. So these are all properties that you should have come across previously in your mathematical career. These two, at least, we did in the review in the last section. So let's go ahead and prove the theorem. What we're going to do is start out by letting capital F of sub t of t be the CDF for t. That means by definition, right, we're going to apply exactly this. The definition here that f sub t of t is the probability that t takes values that are less than or equal to little t. But t now is supposed to be g of x. So I can replace that this is the probability that g of x is less than or equal to little t. Now we're going to use one of these properties here. We have g with an inequality. We're going to go and apply this property here, which means that we can say this is the property, or the probability, that x is less than or equal to g inverse of t. And then take a look. We have the probability that x is less than or equal to some value. That's here. That's the definition where x has been replaced by g inverse of t. So we can say that this is big F, the CDF, f sub x of g inverse of t. Now that's all well and good. That's the cumulative function here. But if we want the density function, well, we can apply our last property. We know that the density function, f sub t of t, is the derivative of the cumulative distribution function. So it is f sub t prime of t. And that we have just calculated is this. So we can replace and say that that is the derivative of f sub x evaluated at g inverse of t. All of that primed. Now we're just in calculus 1. We need the chain rule. So we're going to evaluate the derivative of the outside function, f sub x prime, keep the same inside function, g inverse of t, times the derivative of the inside function. The inside function is g inverse, so g inverse prime, horrible notation, but there it is. And the last thing we can do is simplify. We know the derivative of the cumulative distribution function is the PDF. So we can write this as little f sub x of g inverse of t times g inverse prime of t, and that is exactly what we had in the statement of the theorem. So that is QED, that is what we were asked to show. This proof uses a lot of symbols, right? It has big X, that's a t. It has big X, it has big T, it has little t, it has inverse, it has derivative. You need to make sure that you understand what each of these symbols mean. Taken separately, none of this is difficult. Altogether, it can look like a bit of a jumble. Make sure you take the time to parse it all out, to tease it out, to make sure that you understand what's going on step by step. A little remark. Although this formula, it gives us a formula. The theorem gives us a formula. I never use it. What I do when I need to is I apply this procedure. This formula only applies in very limited situation when g is a one-to-one increasing function. We're going to see in an example afterwards that we don't necessarily need to go this strong. If we're careful, right, what this was about manipulating the inequalities. If we're careful about how we manipulate this inequality here, we can actually use a similar procedure in a situation where g is not one-to-one and increasing. So we'll see that in an example coming up.